Welcome to another deep dive, listeners. This time, we're going exploring the world of adversarial attacks and defenses in deep learning.
Fascinating area, really.
It is, and we'll be taking a close look at a paper called How Deep Learning Sees the World, a survey on adversarial attacks and defenses by Costa, Roxo, Proença, and Inácio.
It's a great survey, actually.
It really is a comprehensive one, so it gives us a really good overview of the current research.
A good roadmap to navigate this field, I'd say, especially for our listeners who are already experts. It gets right to the point.
Exactly. And, one of the things that really struck me right off the bat is how the paper highlights this sort of inherent vulnerability of deep neural networks.
Yeah, it's a bit unsettling, isn't it? I mean, you have these DNNs, highly accurate, performing incredibly well, but they're susceptible to these things called, what are they called? Adversarial examples?
Adversarial examples, yeah. These subtly altered inputs that can completely throw them off.
And what's wild is that these changes, these perturbations, they're often invisible to the human eye.
Right, you wouldn't even know to look for them.
The paper gives this pretty striking example, actually. Uses the smoothfool attack to slightly alter an image of a whale, and it totally changes how the network classifies it.
Yeah, I remember that. Makes you think about the implications for, let's say, self-driving cars.
Oh, absolutely. The real-world stakes are high. Imagine a self-driving car misinterpreting a stop sign because of some tiny invisible alteration.
Scary stuff. So how do researchers even begin to control, the magnitude and type of these tiny changes? They mentioned using something called vector norms, right?
Yeah, vector norms, they're basically mathematical tools to measure the size and characteristics of these perturbations, like L0, L2, LD, you've got your different types.
Okay, and what about that epsilon constraint? I remember seeing that term.
Yes, the epsilon constraint. Think of it as like a limit on the mischief you can cause. It sets a boundary for how much you can change the image.
So it keeps things subtle, basically.
Exactly. Can't just go around completely distorting the image, got to be sneaky about it. And the choice of vector norm combined with your epsilon value, it really influences how effective your attack is.
So you're saying it's not just about, causing random errors. There's strategy involved.
Oh, definitely. The goals of an adversary can vary quite a bit. Sometimes they might just want to reduce the model's confidence, make it less sure of itself.
Right, kind of shake its faith a little bit.
Exactly. Other times they might launch an untargeted attack, just trying to get the model to make any wrong classification, doesn't matter which one.
But then you've got the targeted attacks.
Ah, yes, those are the insidious ones, where the attacker wants to force the model to misclassify the input into a very specific, pre-chosen category.
So there's a specific agenda there.
Absolutely. And then you have to consider how much the attacker knows about the model itself.
That's right. White box versus black box attacks.
In a white box scenario, the attacker knows everything. The model's architecture, its parameters, it's like having the blueprints.
So they can really fine-tune their attack.
Exactly. But in a black box attack, which is probably more common in the real world, they only have access to the inputs and outputs of the model. It's more challenging, but still very possible.
A bit like trying to pick a lock without knowing the mechanism.
Good analogy. And this paper does a great job of taking us through the history of attack methods, showing us how it all evolved.
Yeah, we start with that LBFGS method. That was a big one. Show just how vulnerable DNNs could be to these tiny perturbations.
Right, groundbreaking work. Then you have FGSM, which was a faster, simpler approach. Showed how you could use gradient information of the model's loss function to craft those adversarial examples.
Sort of like laid the foundation for what came next.
Yeah.
And things definitely escalated from there, like with Deepfool.
Deepfool, yeah, that one was clever. Figured out you don't need to change every pixel, just the ones along the decision boundaries.
Smart. Then you have Smoothfool, which we saw with that whale example, creating these smoother, more transferable perturbations.
Transferable, yeah, that's a key point. Means an attack crafted for one model could potentially work on another.
A bit like a universal key.
Exactly. And of course, we have to mention the Carlini and Wagner attack, or CNW. One of the most effective out there, really.
CNW, yep. That one's notorious for its strength. Iteratively refining the perturbation to really maximize that misclassification.
Yeah.
And it comes in different flavors, so to speak.
Right. You've got your L0, L2, LU versions. Adds to its versatility.
It really does feel like an arms race sometimes. But thankfully, the paper doesn't just focus on the attacks. It delves into the defenses as well.
Oh, absolutely. Researchers are fighting back, and they've got a pretty diverse arsenal of strategies at their disposal.
Yeah, the paper breaks them down into 6 key domains. adversarial training, modifying the training process, use of supplementary networks, changing network architecture, performing network validation, and then finally adversarial purification.
6 key strategies, a good way to categorize them.
Let's start with adversarial training, because that seems like the most intuitive approach.
Yeah.
You basically train the model on its own weaknesses, right?
Exactly. Feed it adversarial examples during training, force it to learn from its mistakes.
So it can build up a resistance.
Exactly. And you've got variations of this as well, like ensemble adversarial training.
Where you use adversarial examples from multiple models.
Right. Got to make sure your defense isn't too specialized. You want it to generalize well against a variety of attacks.
What about the techniques that modify the training process itself? I remember defensive distillation sounded interesting.
Ah, yes, defensive distillation. It's kind of like training a smaller network, the student, using the output probabilities of a larger pre-trained network, the teacher.
So like passing on the wisdom, so to speak.
Exactly. Can make the smaller network more resilient that way. And then you've got the approaches that use supplementary networks.
Right, adding extra layers of security, basically.
It's like a security checkpoint, yeah. Magnet and the adversary detection network, those are 2 good examples. They basically try to filter out adversarial examples before they reach the main classifier.
Clever. But wouldn't that add complexity and slow things down?
Well, there's always a trade-off, right? Security versus performance. The paper goes into the different architectures and their, strengths and limitations.
Makes sense. So what about changing the network architecture itself? Can you make it more resistant that way?
You can. Techniques like feature denoising, for example, they add these special blocks to the network to clean up the incoming features.
Like built-in noise cancellation, I guess?
Yeah, exactly. Then there's network validation, which is all about finding those weaknesses before the attacker does.
Important proactive approach.
Like stress testing, making sure your bridge can handle the load. Deep Explore and Deep Gauge are good examples of this.
And lastly, we have adversarial purification, where you're basically using generative models to clean up those adversarial examples.
Yep, using models like DDPMs, denoising diffusion probabilistic models, to try to restore those images back to their original form.
It's amazing how these generative models are finding applications in so many different areas. Okay, so we've talked about the vulnerabilities, the attacks, the defenses, but there's this whole other aspect we need to consider. Vision transformers.
VITs, right.
VETs, yeah. They're rapidly gaining popularity in computer vision, so it's natural to wonder how they hold up against these adversarial attacks.
It's a key question, and the paper does address it. What's interesting is that, VITs don't have this inherent immunity to adversarial attacks.
Oh, so they're not the silver bullet.
Nope. They have their strengths and weaknesses, just like other architectures. They actually show improved robustness against some attacks, like FGSM, compared to CNNs, but they're more vulnerable to others, like CNW and MIFGSM.
Interesting. So it's not a clear-cut victory for VITs in this arms race.
Not at all. And researchers have already developed specific attacks that target VITs, like SAGA, PNA, and patch-out.
But of course, there are defenses emerging as well.
Right. You've got things like patch veto and smooth VITs. It's an area of active research for sure.
It really is a constant back and forth.
Yeah.
So let's talk about evaluation. How do we actually assess how effective these defenses are?
That's where you need robust metrics. Accuracy, fooling rate, average robustness, destruction rate, all of those play a role.
Okay, break those down for me.
Sure. So accuracy is pretty straightforward. How many examples does the model classify correctly? But you got to differentiate between clean accuracy on unperturbed data and robust accuracy on those adversarial examples. A good defense needs to be strong on both fronts.
Makes sense. And what about the fooling rate?
Fooling rate tells you how often the attack succeeds in tricking the model. Higher fooling rate, more vulnerable the model. Then you've got average robustness, which gives you a more holistic view.
Oh, so?
It measures the average perturbation needed to fool the model, gives you a sense of its overall resilience, and then you have the destruction rate.
Okay, what's that one measure?
That one looks at how much an image transformation, like let's say blurring, can disrupt the effectiveness of the attack.
Interesting. So you have all these different metrics to give you a well-rounded assessment.
Precisely. And then, of course, you have to think about the data sets you're using for evaluation. The paper covers quite a range, from MNIST and CFAR 10 to CFAR 100 and ImageNet.
Yeah, they're not all created equal.
Nope. A defense that performs well on MNIST might not be as effective on ImageNet. Got to test across different data sets to get a true sense of its generalizability. And what's interesting is the paper points out that while research on MNIST and CFAR10 is pretty mature, research on those more complex data sets like CFAR 100 and ImageNet is still lagging behind.
So there's a lot of room for growth there.
Oh, definitely. The defenses on those more complex data sets haven't quite reached the same level of accuracy. Lots of work to be done.
So let's get to the chase. Based on all of this research, which defenses stand out as the most robust, the most effective?
Well, adversarial training is definitely a top contender.
Not surprising, considering it directly exposes the model to those adversarial examples.
Right. It's like facing your fears head on. And the paper emphasizes the importance of using strong adversarial attacks during training, PGD, auto attack, those kinds of things.
To ensure that robustness, to make sure it's not just overfitting to a specific attack.
Exactly. You want a defense that can handle a variety of threats.
So what about those other approaches beyond adversarial training? Are there any that are particularly promising?
Definitely. Using supplementary networks and modifying the training process, those have shown some very encouraging results. Like DISCO, which uses a supplementary network for adversarial purification, that one's achieved good robustness on CFAR10 and ImageNet.
Disco, okay, I'll have to look into that one.
And then there's ODF, which leverages these stable neural ODEs to modify the training process. It's shown excellent performance on CFAR10 as well.
So there's no one-size-fits-all solution?
Nope. It's about finding the right combination of defenses tailored to your specific needs.
All right, well, we've covered a lot of ground here, but I want to look ahead now. What are the big open questions, the exciting future directions for this research? What did the paper highlight?
Well, for starters, they really stressed the need for standardized evaluation on auto attack.
Okay, auto attack, I remember that being mentioned.
It's a powerful attack, combines multiple attacks, including black box ones, and they're saying we need to use robust accuracy as the main metric when evaluating defenses against it.
So it's about creating a level playing field, so to speak.
Exactly. You want a standardized framework so you can accurately compare different defenses. And then, of course, they emphasize the need to move beyond MNIST and CFAR10.
Right, those more complex data sets we were talking about.
CFAR 100, ImageNet, SVHN, GTSRB, Fashion MNIST, all of those need more research. We need defenses that can handle those more challenging data sets.
Makes sense. Any other key directions?
Yeah, they also called for the development of a standardized metric to actually quantify the amount of perturbation being added to an image.
Oh, interesting. So we can compare apples to apples, basically.
Exactly. Right now, it's a bit difficult to compare across different data sets and different attacks. A standardized metric would make things a lot easier. And on the attack front, they advocated for a shift in focus towards black box and gray box strategies.
More realistic scenarios, since you rarely have perfect knowledge of the model in the real world?
Right. And then, of course, there's the whole question of network architecture.
With the rise of VTs.
Exactly. Can we leverage the unique structure of VTs to build inherently more robust models? Lots of potential there. And they also highlighted the need for real-time adversarial purification strategies.
So techniques that are fast and efficient enough for real-world applications.
Exactly. Like self-driving cars, where split-second decisions matter.
Well, this has been an incredibly insightful deep dive.
It really has a lot to consider.
We've only scratched the surface, really. But we've laid a good foundation.
Yeah, we have. And it's clear that this field is, it's rapidly evolving, full of challenges, but also full of opportunities.
I'm definitely going to be digging deeper into this.
That's the spirit. And who knows, maybe you'll be the one to make the next big breakthrough.
Well, let's not get ahead of ourselves.
Yeah.
But it is fascinating stuff, and it has the potential to really shape the future of AI.
No doubt about it. It's been a pleasure diving into this with you. Let's pick it up again next time. It really is a dynamic field, this constant back and forth, attackers and defenders. It's driving some amazing innovation. And, the deeper we dig into this stuff, the more intricate it gets.
It is fascinating. And one of the things that really stood out to me was this concept of universal adversarial perturbations, or UAPs. The idea that a single perturbation could fool a model on, a bunch of different images is kind of mind-blowing.
It speaks volumes about how, neural networks learn features. I mean, Musavi Desfouli et al. Kaki's work on UAPs, that was groundbreaking stuff. They showed how these perturbations can exploit certain directions in the input space and just consistently lead to misclassifications no matter what the image actually is.
So it's like finding this master key that can unlock a bunch of different doors rather than needing a specific key for each one.
Perfect analogy. And what makes it even more concerning is that these UAPs, they can generalize across different neural networks.
Oh, so it's not just, specific to one model.
No, means an attacker could potentially craft a single perturbation that could disrupt a whole range of models. And then you have the universal adversarial networks, or UANs.
UANs, right. Networks designed to generate UAPs.
Exactly. They're trained on existing UAPs, learn to create new ones. It's like, the arms race is escalating, defenses evolve, attacks evolve.
A never-ending cycle.
Pretty much.
So let's shift gears a bit and talk about those defenses again. We touched on adversarial training earlier. Can you give us a little more detail on some of its variations?
Sure. So we mentioned ensemble adversarial training. That's where you use adversarial examples from multiple models during training.
Right, to make sure the model isn't just overfitting to a specific attack.
Exactly. It forces it to learn these more robust, more generalized features.
Right.
And then you have trades, which stands for, get this, trade-off-inspired adversarial defense via surrogate loss minimization.
Catchy. What's the idea behind that one?
It's all about finding a good balance between robustness and accuracy.
Because sometimes making a model super robust can actually make it perform worse on normal data, right?
Right. And trades tries to minimize both types of errors, the natural error on clean data and then boundary error, which measures how close those input features are to the decision boundary.
So it's like creating this buffer zone around the decision boundary,
Right.
making it harder for those adversarial examples to push the input into a different class.
Exactly. And then there's MART, misclassification-aware adversarial training. That one's a bit more targeted in its approach.
How so?
It treats misclassified examples differently than correctly classified ones during training, uses different techniques for each case.
Interesting. So it seems like adversarial training, with all its variations, really plays a central role in this whole, robustness thing.
It does. But, those other defense domains have some interesting stuff, too. We talked about supplementary networks before, like Magnet.
Right, the multi-layered security system approach.
Yeah, using multiple detectors to try and catch those adversarial examples.
Remind me how that works again.
So basically, you've got these detectors, and they're trained to identify different types of adversarial examples, some that are, heavily perturbed, others with more subtle changes. And if a detector flags an input as suspicious, it can either be rejected outright or, passed on to a human for further inspection.
So like a human in the loop, just in case.
Exactly. And then there's Defense Jan, which uses, you guessed it, generative adversarial networks.
JANs, those are everywhere these days.
They are. And in this case, the Jan is trained to learn the distribution of clean data, so it can basically purify those adversarial examples, remove the perturbations, and bring them back to normal.
Kind of like a digital detox for those adversarial examples, removing the bad stuff.
I like that. And then on the architectural front, you have techniques like feature denoising, where you add those special blocks to clean up those features.
Noise cancellation, right?
Exactly. And then there's the sparse transformation layer, or STL, which transforms the input image into a lower dimensional space that's designed to be more resistant to those perturbations.
So like squeezing out the noise.
Exactly.
Out of all these defenses, is there any one in particular that you're really excited about, one that you think has the most potential?
I'm really intrigued by adversarial purification, particularly those methods using DDPMs, those denoising diffusion probabilistic models. They're really good at capturing the distribution of clean data, which makes them incredibly effective at removing those perturbations without messing up the image itself.
We talked about them before, but what makes them so good at this?
They're just amazing at learning the nuances of clean data, So they can really distinguish between those true image features and the adversarial noise, and then they can selectively remove that noise without damaging the original image.
It's like having this digital art restore, someone who can carefully remove all the imperfections and reveal that pristine original underneath.
Beautifully put. And the paper highlights some recent work using DDPMs for adversarial purification with some really impressive results. I think they hold a lot of promise for the future.
Definitely something to watch. Okay, so we've gone through a lot, the vulnerabilities, the attacks, the defenses. As we head into the final stretch of this deep dive, what are the big takeaways here, the big picture things we should keep in mind?
Well, the big picture is this. Adversarial attacks and defenses, they're constantly evolving, and they have real implications for the future of AI. What we've learned is that, firstly, even those highly accurate DNNs, they're vulnerable.
No such thing as perfect security.
Right. And secondly, those attacks, they're getting more and more sophisticated. UAPs, UANs, they show us that this threat is constantly changing.
It's a moving target.
It is. But the good news is, thirdly, we're developing more and more defenses. Adversarial training, supplementary networks, generative models, we've got options.
It sounds like the best approach is probably, a multi-layered one, combining different techniques.
Absolutely. And of course, you need that rigorous evaluation, using those robust metrics and those diverse data sets to make sure your defenses are actually working in the real world. And fourthly, we need to remember that this field, this whole area of research, it's constantly evolving.
So we got to stay on our toes.
Exactly. New attacks, new defenses. It's a never-ending game of cat and mouse.
Which brings us to, the bigger picture. This research, it has real-world implications. It's not just theory. It's about how AI is actually being used and how it could potentially be misused.
Absolutely. Adversarial attacks, think about it. They could be used to manipulate AI systems in some pretty dangerous ways.
Yeah. Give me some examples. What are some scenarios that, keep you up at night?
Well, imagine a self-driving car, right? And it gets tricked into misinterpreting a traffic sign. Leads to an accident. Or what about facial recognition systems? Someone could fool them into misidentifying a person, and that has huge implications for security and privacy.
It's a bit scary when you think about how much we rely on these systems already. And as they become even more integrated into our lives, the stakes just get higher.
No doubt about it. That's why this research on adversarial defenses, it's so important. We need AI systems that are not only powerful, but also, trustworthy.
We need to be able to rely on them.
Exactly. But it's tricky because, like we said, those attacks are always evolving.
So it's almost like a cybersecurity battle, constantly trying to stay one step ahead.
That's a good way to put it. And it's not just about technical solutions either.
What else is there?
Well, we have to think about the policy implications, the ethical implications. We need guidelines for responsible AI development, for responsible AI deployment.
So it's not just about building better defenses. It's about making sure that those defenses are used for the right reasons.
Exactly. And making sure that those who try to misuse these attacks, that they're held accountable. This research, it raises some really fundamental questions about AI, about its trustworthiness, its reliability, its security.
Big questions, no easy answers.
Nope. But they're important questions.
Well, as we wrap up this deep dive, I'm curious to hear, what gets you excited about this field. Where do you see the most potential for, those groundbreaking advancements?
One area that I find really fascinating is the potential of adversarial training to not only make those models more robust, but also to help us understand how those models actually learn.
Oh, interesting. How so?
Well, when you see how a model reacts to these adversarial examples, it can give you insights into its internal representations, its decision-making process. It's almost like you're peering into that black box of deep learning and trying to figure out what's going on inside.
So it's a tool for explainability as well.
Exactly. And I'm also really excited about those new defense mechanisms, especially the ones using those generative models, like those DDPMs we talked about. Their ability to kind of clean up those adversarial examples to generate synthetic data, it opens up all sorts of possibilities.
Yeah, there's a lot of potential there.
A lot of potential. And despite the challenges, I'm optimistic about the future of this field. I really think that through research, through collaboration, we can develop AI systems that are both powerful and trustworthy.
It's a good note to end on.
It is. And, this deep dive, it's just been a small glimpse into this field. There's so much more out there to explore.
Well, I'm definitely going to be doing some more exploring, and I hope our listeners will too. Thanks for this amazing discussion. It's been a pleasure.
The pleasure was all mine. It's always fun diving into these complex topics with you. And remember, everyone, the pursuit of knowledge, it's a journey, not a destination. So keep exploring, keep learning, and keep pushing those boundaries of what's possible with AI.
Well said. Until next time, keep those minds curious and those algorithms robust.